Welcome to Decoding the Data Ecosystem, a podcast with valuable insights, inspiring stories, and practical advice to guide you on your journey through the world of omics research and how the NIH Common Fund data ecosystem can support that journey. I'm your host, Dr. Allissa Dillman, and I'm the Training and Engagement Director of the CFDE Training Center. My background's in bioinformatics, and I've been working in bioinformatics and data science training and engagement space for almost the past 15 years. I'm really passionate about lowering the barriers of entry for these fields through creative engagement activities such as these podcasts. Now let's get to the show. Today I'm talking with Dr. John Kwagyan, a statistician, graduate associate professor of public health, master of public health program at Howard University, and adjunct associate professor of Johns Hopkins School of Medicine Oncology Center. He also serves as the co-director of Biostatistics, Epidemiology and Research Design core at the Georgetown-Howard Universities Center for Clinical and Translational Science. He does research in clinical trial health outcome, survey analysis, meta-analysis, and predictive modeling. John and I met actually a couple of years. We met a couple of years back on the virtual data science program called BADSTI. So I'm really excited to have you on the podcast today so we can talk a little bit more about the work that you do. So tell us a little bit more about yourself and what you do.
Thank you, Allissa. As you said, I'm a professor, associate professor at Howard University, and also co-director of Biostatistics, Epidemiology and Research Design component of the Georgetown-Howard University Center for Clinical and Translational Science. Basically, my research area is in correlated data, predictive models, data analysis, and then I apply those with application to diseases common to minority population. So in Nigeria, that is what I do.
So I was hoping to talk to you today a little bit about a topic I think everybody is always really buzzy about, and that's AI. So I was really curious to hear your thoughts on, what you think the promise of AI and machine learning in genomics and personalized medicine is, and what you think about that.
Yeah, thank you for the question. I mean, we are in this time of the world where things are so much technological with those advancement in technology. So with this advancement in technology, we are able to generate huge amounts of data sets. And then once these data sets are generated, then of course we have to be able to analyze it. So we analyze this using AI machine learning to accelerate research, ultimately leading to a more preventive and proactive healthcare. So with AI and machine learning, we are able to analyze genomic data to identify genetic variations associated with specific diseases, leading to a more precise and timely diagnosis. We can also predict individual responses to medications, enhancing precision medicine. We can identify potential drug targets and predict their efficacy, accelerating the drug development discovery process. AI algorithms are also being used to analyze medical images faster and more accurate than human doctors or radiologists, if I may say, which will lead to early detection of diseases such as cancer. So the promises are many, but I can summarize it here and say that AI and machine learning offers transformative approach to genomics and personalized medicine, promising more accurate diagnostics, faster drug discovery, and tailored treatment plan based on individual genomic profile.
So I'm really interested, so that there's lots of different types of omics data, genomics, transcriptomics, proteomics. Out of all of the different types of omics data, are there some that are especially amenable to AI and machine learning approaches? And why is it that like potentially some of these data types are more amenable?
Well, once we're talking about data, then data either is coming from the biomedical field, industry, finance, whatever is still data. But in genomics, it's a special one because in genomics, we are able to generate vast amount of data, as I've said earlier, because of the advancement of high throughput technologies that has enabled researchers to generate vast amount of complex omics data. As we said, this data includes for genomics, transcriptomics, proteomics, metabolics, epigenomics. All these are huge data sets. And then we have this to gain a comprehensive understanding of complex biological systems, identifying biomarkers, classifying diseases, developing targeted therapies, and enhancing personalized medicine. So they are all almost the various types of omics data are amenable to AI machine learning approaches. If we take genomics, for example, AI machine learning approaches are applied to analyze DNA sequencing data, classifying genetic variants and their association to disease risks. If we take transcriptomics, AI and machine learning approaches are used to analyze RNA sequence data, identifying differentially expressed genes to examine, among others, genes that are up or down regulated and their association to disease risk. So similarly for proteomics, AI is employed for analyzing the quantitative and sometimes also the qualitative changes in protein expression on the different conditions. So the list goes on and on. So similarly for epigenomics and then the other types of biomarkers in omics research.
So when I think of the different types of data, the sequencing data, I think about sort of their outputs. You know, for instance, with genomics data, you're looking at every base and looking at whether there's a variant or not a variant. So at the end of the day, it's kind of a little bit binary for every position versus something like transcriptomics, where it's really about expression levels. So there's a huge dynamic range, especially for some genes versus other genes. So those, just like even thinking about those two types of omics data, like they have very different outputs of like what you're measuring. But like the thing that I've noticed is more commonly genomic data is really what people use a lot for machine learning. Um, and is there something about that for you anyway? Do you think there's something about genomic data that's like particularly well suited, or is it just that it's more actionable what the results are, or what are your thoughts on that?
Yeah, I would say I think it all will depend on a person's area of research, whether they are uh, uh, whether it's what epigenomics or uh, or or genomics or transcriptomics. So it depends on the area. I mean, I have colleagues who do their research uh, in epigenomics. So I've been associated with him, and then I find it interesting. Now, all the data, of course, they are all huge data sets because it's genes, but there are different types. For example, as you mentioned, if it is transcriptomics, we'll be looking at what gene expression levels, which makes it a quantitative data. If it is uh, uh, gene variant, then we'll be looking at what DNA sequences, we'll be looking at what mutations, and then normally the focus is what is in classification. So that also gives us a different types of data set, which in this case is going to be a qualitative or categorical. So either is gene expression or levels, or is gene variant. The approaches are there. So again, if I go back to statistics or the traditional statistics, we have different types of data set, and then for each data set, there are approaches to answer them. So it's not a question of which one is suitable. Either one of them will be suitable because it's data at the end of it, and then AI and machine learning approaches are suitable for those.
So you talked about different models or different algorithms, and I'm curious to have a little more of a deep dive on like which types of algorithms are most often used in genomic prediction tasks, and why are those kind of the most commonly used approaches?
So again, it will depend on the task ahead. Of course, machine learning, AI is broader. It's even becoming much broader. Now, if you are looking at the literature, the one that are commonly used these days are what it will be the random forest algorithm, and then the support vector algorithm. So those are traditionally being used a lot, but now we are even using what we call the ensemble learning techniques. Ensemble just means that we are combining different algorithms to achieve one purpose. As a matter of fact, random forest algorithm is an ensemble approach. Random sample basically is what? It's a combination of various decision trees, because one of the algorithms for classification is decision tree. So if you are talking about each individual ones, then random forest is used, support vector machines are used, and then they are good to use because they are both they are robust to overfitting, which is one of the common challenges in AI machine learning approach. And then also dealing with what the high dimensionality of the data. So those are the two commonly used, but as I said, they are commonly used, but there are so many different algorithms coming up, and then many people are relying on the ensemble techniques rather than just one single approach. Because the purpose of using the combination approach is what? Is to gain power, is to increase the predictive power of the algorithm. And in many cases, that is one of the key reasons why we use machine learning algorithms. We want to be able to predict an outcome, whether it's a risk to a disease or some other condition.
So you'd mentioned overfitting, and I'm curious, is there like unique challenges of overfitting specifically when dealing with genomics data? Is there particular risks that are unique to genomics data and overfitting just because of the vast amounts of information you're getting from each patient?
Yes, overfitting basically means that the model, because machine learning approaches are data dependent. So if I have a data which is large, huge, high dimensional data, overfitting means that the algorithm is going to do excellent and then train the data and then predict the outcome that is being researched very well. You're going to have a very high predictive power. But that is all that it can do. But once I have a new data set that is unknown, then that program or that algorithm is not going to do well there, which means that because I have this just one data set, it's large, I'm able to fit it very well, but that is only for that particular data set. It cannot, we cannot replicate it on a different data set. That is the concept of fitting, and that is one of the concerns in AI machine learning algorithm. And then, of course, as I said, one way to check that is to use this ensemble approaches.
Is there, if you're sort of analyzing, genomics data separately on its own or transcriptomics separately on its own, is there a difference between doing any of these data types just individually versus if you're actually interested in doing a combination analysis? So if you want to actually integrate something like, say, gene expression and variant data together, as part of a precision medicine, is there something unique about this integration?
I think what is unique is the integration itself. Now, the analysis approach, one that is done because we are integrating, which means that even sometimes the data set may be at different places or in different databases. So being able to access the data, linking, and then integrating them, that is a challenge. But once you come to the analysis itself, what is the output data and what are the input data? So if the inputs are, let's say we have gene variant data and gene expression data, do you want to include both of them in the analysis? Because doing so becomes what? I mean, that will compound the massive data itself, because as I said at the beginning, genomic data by nature is very huge. So if you are integrating two of them, that compounds it. But for the analysis itself, using ensemble approaches will be better, again, to be able to increase the power of the model. For what is it? Because one of the key things in machine learning is searching for a model rather than starting with a model. That is why in many cases, if you see people using machine learning, they are going to present several models and then compare the predictive accuracies of those. But of course, you have to know where to start. If it is a classification problem or a classification task, then we are going to use for several classification models to be able to decide on which of them gives us a better predictive power.
So I'm curious to dive a little deeper into how exactly do machine learning models use genetic information to predict disease? Like, are there particular features that are most informative for these models?
Yeah, of course, it's genetics or genomics. So that by nature gives us what? This huge data set with so many different genes or SNPs and other things. So a particular feature, of course, the genes themselves, if we are predicting disease risks or even response to therapy, then the input variables or the features are going to include what? Include the genes or the SNPs or expression levels. So what we do, or what even as I mentioned before, a random forest, for example, one of the key use of random forest is to be able to identify informative features. So if you start with random forest, you're able to identify the informative feature, then you can use that on using another approach to continue with it, or to continue with the analysis to see which ones are going to give us the best predictive approach. Of course, so that will what, if you are using random forest, then we are going to what, map the complex association between the genetic variations or SNPs with the disease types or the disease phenotypes. Or we do what we call what, feature engineering. Feature engineering is just say that I have all these features here, which of them are the most informative. So again, you can start with one model and then combine it with others and continue with this. Of course, sometimes also we have to what, integrate the genetic features with other biological markers if they are relevant to that study.
So you mostly talk about SNPs, so single nucleotide polymorphisms. Are there certain variant types that behave better in the models that you're talking about? I mean, is it just that because SNPs are sort of these single variants that they're easier to build models for than, say, structural variants? Or is there a reason why I'm not seeing as much for structural variants? Or other kinds of variants, like indels, for instance, as well?
Yeah, I'm just speaking to this in general terms. So now whether it's going to be structural variants and other things, then that will depend on the particular research that the person is doing. So it doesn't even have to be SNPs. It can be maybe just even looking at what genotypes. Or sometimes we can even just look at the allelic structure in the model. So what you put in or what you decide on is going to depend on the particular research that the researcher is pursuing.
Okay, I see. Thanks for that clarification. I was curious to know if perhaps structural variants were sort of harder to navigate. Um, I'd love to know, is there a particular case in your own research where you used either AI or ML that really led to meaningful insight in a particular disease area? Like, do you have kind of a favorite example in your own research that you'd like to walk us through?
This is what I'm going to say about this. I think last week or 2 weeks ago, I came across this paper that was published last month, May 2025, in the European Journal of Medical Research. So basically what they did was they reviewed data over the past 10 years, and then they came up with what they found 16 diverse diseases that demonstrated remarkable accuracy and efficiency of machine learning approaches in disease prediction and diagnosis. Of course, these days, the use of AI-enabled wearable devices are on the rise, and the use of those have facilitated remote monitoring of patients and early detection and intervention. I have one colleague. He is in the school of, he's a computer science in the school of engineering, and he published a paper just using machine learning approaches to predict risk for cardiovascular disease. And what I found even more fascinating was what he was doing this using what social media data, which means he had to use large language models. And I was surprised to see how just using large language models he was able to have what high accuracy just based on what those individuals are saying on their social media platform. So the uses are many. I mean, there are several many cases. In my own personal case, I have issues with sleep apnea, and then I wear CPAP monitor, which is paired to my iPhone with an AI-enabled app, and be able to monitor my sleep patterns and manage my sleep conditions. So before even I meet the doctor or the expert, he already knows everything about my sleep patterns. So machine learning AI, they have been very innovative, or they are able to give us much insight into our specific disease areas.
So there's this term that comes up, explainable AI. I'd be curious if you could sort of break down what exactly specifically explainable AI is and why it might be specifically important in genomics.
Well, explainable AI basically refers to models and techniques that make it clear and why an AI system produces certain results. It's a little broad. Many people are talking about this these days in research areas. But mainly what it tries to do is, if you take a simple statistical model like a logistic regression, which is also one of the classification models in machine learning, many people can even write the formula, everything, and then we'll be able to interpret the result. That is not quite clear in machine learning. That is why the emphasis has been on what we call explainable AI. I have been in talks on machine learning, even sometimes if I'm invited to graduate a student presentation on AI or machine learning. Many of them are going to run the model and then have several models and then tell you that among this 1, 2, 3, 4 algorithms, this is the best predictor, or this one gives us or will provide the best predictor. Now, if I throw a question to them that, okay, in your model, I see you have gender in there, you have ethnicity in there. Can you tell me which of them or how gender makes a difference? Many times they are not able to do that. They are not able to explain it. They are not able to interpret the parameters. So that has been a concern that I've, as a matter of fact, discussed it with so many people, that we don't just end at the identifying the best predictive model, but once you're able to do that, how is that going to help the clinician? Let's say you have BMI in there or age in there. How are you going to or make the clinician able to decide that, okay, maybe if you are an African American or from a certain ethnic group, then your risk is higher than other things. So basically, that is what it is. I mean, in the simpler terms. But if you are going into the deeper terms, then people want to be able to understand. For example, neural networks. The term used is what? Is an approach in a black box. So it's kind of, okay, so in a black box, so we don't even have to worry ourselves about knowing what exactly is going in there. So that is why research or researchers are talking more about explainable AI, that, okay, how are we able to understand what is going on that is giving us this model, or determine this is the best predictive model and then how are the clinicians going to use the data to make decisions?
I did want to back up a little bit, and actually, you
Yes.
mentioned, some specific statistical models, and so I'm curious to know, what really for you is the difference between machine learning and statistical learning?
Machine learning and statistical learning, they are closely related, but they have different approaches and goals. As a matter of fact, statistics is a whole big chunk of machine learning, but the approaches are different. Statistical learning will probably just focus on what? Understanding relationship between variables. Maybe they will be interested, more focused on what hypotheses are testing, which means that they have to evaluate assumptions about the data to select or use the best statistical approach. Machine learning, on the other hand, focuses on prediction, classification, and learning. I mean, if you have seen learning, because in machine learning, we use what? We have the supervised and then the unsupervised approaches, which means you have to split the data into two aspects, train the data on part of the, on a subset of the data, and then use it for prediction. So the key difference is machine learning focuses more on the predictive performance using a general purpose learning algorithm, whilst statistical learning focuses more on for the relationship between the variables. And so that, as you mentioned, if I have age in the data, I have gender in the data, you should be able to describe the relationship between gender and then the variable, rather than just focusing on the predictive performance. So the advice is that, I mean, if you're able to comprehend both of them, that normally makes the researcher or the AI ML researcher, make them more or better informed on what approach to use.
So when you were talking about explainable AI, you're talking about, you don't want a black box, and that kind of, and you were talking about, especially in like in medical settings, and that kind of makes me think about, what kind of ethical considerations are there when using AI or ML in genomics research?
Well, there are several ethical considerations or ethical concerns. So, of course, data privacy and confidentiality is one ethical concern in all aspects of research. Of course, genomic data is highly sensitive and personal, so protecting it from unauthorized access is crucial. Another topic that has come up recently is data ownership. If someone is doing genomic research, or for that matter, any type of research, who owns the data? Who owns the data set? Is it the researcher? Is it the sponsor? Or who owns it? So data ownership has become a question. And then I'm glad to, or the good news is that these days, many research centers have what is called what community engagement components. And what this community engagement component do is to involve the community leadership in making ethical decisions. I mean, you have to sit down with them, you have to let them know. Of course, another ethical concern is for transparency. They have to know everything that is going to be done with the data, including the type of data that is going to be collected, what will be reported, and even if it is genomic, for example, where a sample is drawn or some kind of a biospecimen is taken, if doing research A, you let the participants know that you are going to do just a gene expression analysis. Now you have the sample. Are you going to destroy the sample after 4 years, after 3 years, after so many years? Or are you going to keep it and then use it at another time? These are all ethical concerns, or in this case, transparency that the community, the study participant needs to be aware of. And what are the other ones? Of course, the other ones too are what? Of course, they shouldn't be biased in reporting. We, as researchers, we have to report what the data is saying. Another ethical concern that has been talked about recently is what is algorithmic bias. And what is algorithmic bias? Because these machine learning approaches are data dependent. So if the data contains all Caucasians or Hispanics or African Americans, then the model is going to be trained just based on those. And that could pose ethical issues. That doesn't mean that that cannot be done if maybe the research area is all Caucasians or all African American. That is what is expected. But in the reporting, it has to be very clear that these are the population that were studied. So these are all ethical issues that needs to be addressed carefully and properly.
That's a lot of different potentials for, bias and considerations. And that makes me kind of think about, what do you think are the skills that future researchers will need to really navigate and thrive in this, AI genomics landscape?
Oh, the skill sets are many. I would say that if a future researcher will have to know the technical expertise, I mean, if it is programming, software engineer, even sometimes data expertise, because we want to be able to interpret some of the output and then make sense of those. Of course, there is also what if it is genomic analysis, then it has to be what the genomic knowledge itself. You see, that is the domain expertise. Another thing, another skill set is what is collaboration. In this case, interdisciplinary knowledge. But the beauty of it is all the things that I've mentioned, I mean, the technical expertise, that doesn't mean that if I'm a researcher doing, I have to know everything. That is why the importance of team science is great, or the importance of what a collaboration is great. I'm a statistician, I'm a mathematician, I know a lot of data science, but I may not know everything. So if I have a team or interdisciplinary team, then together we do what? We work together. That's why anytime I'm giving speeches, I let people know that everybody in the room there is what? It's a data scientist, not only the person giving the presentation. One may not know how to program in Python or R, but they may have other knowledge. But the other key skill too is what? I mean, what sometimes they are called what? Soft skills is what? We have to be able to adapt, and then every researcher have to be what? Have to be a lifelong learner. Because we don't know everything, but we have to also devote our time to be able to learn certain things, so that at least if even you are not using it, if you are sitting in an audience at a conference or presentation, you'll be able to understand it. Or even with your research team, you'll be able to understand some of the concepts that is being discussed.
I will say that that's what I really love the most about this field, just how fast-paced it is and how much it really does require you to constantly be learning new things. And that definitely really appeals to sort of my approach to science. So I wanted to end with sort of a silly question. So as a statistician, John, do you have a favorite statistical test or model?
Um, I mean, if you ask me, I would say that in terms of research, my research area is in clustered or hierarchical data. So with all the students that I had, I mean, my undergrad it was in mathematics, a bachelor's in mathematics, also even a master's in applied mathematics. And all the students that I directed were in the mathematics department. So if I'm doing my own research, that is what I try to focus on. But that doesn't mean that I don't do other things. I never took a class in meta-analysis, but at one time, even at Howard, probably even still, I'm the meta-analysis expert there as part of the Georgetown-Howard University Center for Clinical and Translational Science. I have the meta-analysis workshop at Howard, and then we had about 90 individuals from both sides registered for it, and I think about 60 or 60 plus attended it. This was during the before the COVID, so at that time everything was in person. So if one is in a research environment, yeah, you can focus and then do the things you love to do. But again, maybe because of the nature of my job as a statistician, if you are a statistician, you are supposed to be able to know a lot of things so that we can be able to communicate with the clinicians. So if something comes up and then I see an interest in it, then maybe with this data set that Dr. A or Dr. B is providing, maybe I can use this approach and then I will attempt to pursue that. And then if I get somewhere, I just let the Dr. A or Dr. B say that, hey, you sent me this data set here. I've done all the analysis, but I want to apply this my approach or methodology to this data set. So if the person gives the go ahead, which they've done 100% of the time, then I would do that. So I wouldn't say I have any specific, of course, I like what I like a binary outcome, that is disease outcome, yes or no. So once that is the task ahead, yeah, that can easily be done, whether it's clustered data or not. But other things, as they come up because of the nature of my work, I will have to get involved with.
Well, thank you so much, John, for spending some time with us today to talk through some, topics around genomics and machine learning and AI. We really appreciate your time.
Thank you, Allissa.
Thank you. Bye. You have been listening to Decoding the Data Ecosystem, a CFDE Training Center podcast. Be sure to check out our other episodes in this series. Find out more information about CFDE data and tools that may be valuable to your research by visiting our website.